So we begin this, again, the Gaussian plume distribution that we are discussing of. So there are a few interesting things to observe here. What we essentially discuss about this Gaussian plume. So if you see this plume here, just suppose you are taking a cross section of the plume. At any point, you are taking a cross section of the plume. You see cross section of the plume along its line of travel. So this is traveling, say, the plume, as we have already discussed about the plume taking a shape like this. Let me consider that we are taking an imaginary cross section inside this. So what we observe here is what is under this Gaussian plume distribution is one thing that it says is that across this, see here, this particularly at this point, if you just observe in this projection here, if you just make a projection here, it would be, it says the distribution is completely normal. That means it would be having a mean, and it would have a standard deviation, and this is across the center line. So this is, say, this is along the center line. This is along the center line. This is mu. This is this. This is 2, or say whatever. Say just say 3 sigma. This is 3 sigma here. This is what is 1. This is, say, across. This is across. See, if you can say this is sigma z. This is sigma z. This is one thing. But there would be across. This is one part. There would be another along this also. This would be following, so another normal distribution. It would be always a normal distribution, which is the center line. From the center line, say this, from the center line, from the mu, again on the center line concentration at that point of time. This would be here. This is again a sigma x. Sorry, sigma x. This is sigma z we have written in the first place. This is sigma x, and also along, if you can just observe this, also along the same, also along this, the y direction, also along the y direction, it would also have a normal distribution, which is, again, as you can see, we will have a mu. The mu, as we know of, and then this is sigma y. This is across the center line. This is about the center line. So this is where it is. The center line is the center line. So this is, so what it's observed is across x, y, z direction, it will follow a normal. The concentration of the gases would follow a normal distribution. And this normal distribution having a particular mean and standard deviations. Standard deviation across x direction as sigma x, across y direction as sigma y, and across z direction as sigma z. So this is what is the major assumption of Gaussian plume distribution. To observe, when you are saying a plume and when we are saying a Gaussian plume, the essential difference is that in the Gaussian plume we consider that at x, y, z direction, the concentration of the pollutants, concentration of the gases or the pollutants are distributed. They are distributed in a normal distribution, and each of these cases in x, y, z direction, it will be normally distributed. At any point, at any cross section, or at any point, if you take this would be a x, y, z, in the x, y, z direction, a normal distribution around a mean, and the mean would certainly reside at the center line. Mean would reside in the center line. So here itself, so this is the Gaussian plume the distribution that we generally discuss. I think I have made the distinction between a plume and Gaussian plume. The Gaussian plume would be considered like this, and this there are other assumptions are the rate of the initial upward velocity of discharge of the gaseous substances will remain constant during the calculation period. Initial upward velocity of discharge of the gaseous substances will remain constant during the calculation period. Say whatever calculation we are trying to do, I mean it can change, but essentially with that the mu and the sigma x, sigma y, sigma z also changes. Okay, this is number one. This is number one. This the number two is this. The number two is this. The rate of emission. Rate of emissions from the source and the source is constant. Third, wind speed is constant both in time and elevation. The pollutant gaseous and particulates is non-reactive so it is to say it is not lost. It is not lost by decay. Say lost by decay, something like a radioactive substances that we know of, they can decay during the discharge, during the suspension. No chemical reaction. Lost by decay, chemical reaction. That is, they would not be oxidized or they would react with another substance to form a different compound. This will not happen. Remember this. So it is not lost by decay. Chemical reactions of any kind, say which would lead to chemical reactions like oxidation or forming other compounds, right? Chemical reactions or deposition. It also assumes that when it sorry, when it hits the ground, nothing is absorbed, all is reflected. So, all is reflected and all is reflected, all is reflected. So, this is number 5 is is a the terrain is flat, terrain is relatively flat. The Gaussian plume dispersion model is applied universally to estimate Gaussian plume dispersion model is applied universally to estimate the ground level concentration to estimate the ground level concentration of pollutants or airborne pollutants or air pollutants, ground level concentration of the pollutants wherein the humans and most other living beings reside. Say this is this is an universally applied model. It's essentially a good model to start with. I mean, it says mostly even in cases like in the most of these advanced websites, if you make a search, say something like US EPA that I have said, if you just observe, they are still calculating. Most of the cases they are still calculating the ground level concentration depending on this model also. There are certain changes that have been made, but some adoption has been made, but mostly all the models of air dispersion models basically revolve around the Gaussian plume distribution. Okay. So, the Gaussian plume dispersion model is applied universally to estimate the ground level concentration of the pollutants wherein the humans and most other living beings reside. So, if you are trying to measure, suppose if you have seen a power plant and you are saying that it is discharging the pollutants like in the form of CO2, SO2, particulates, NOx, and you want to estimate the ground level concentration, say from 2 kilometers from the plant, or say 5 kilometers from the plant, or even say 500 meters from the plant. In such cases, the most applicable model is Gaussian plume distribution model. Most people use them without reservation in most cases. So, having said this, we will like to explain this, make a relatively what we have said here is, if you just observe this, let us make another drawing here. I mean, as you can see, as I have already explained, is this case, as you can see here. say if you are just trying to observe it like this, I have already said this, but let me pictorially represent this. This is, I have already discussed, I have already told you about all this, but let me just give you a further on this. This is the z direction. This is the z direction that I have already said. This one is the x direction, and this one is, as you know, is y. Okay. So, and if this if the dispersion is taking place, if the dispersion is taking place like this, as per our explanation, as per the explanation that I have already made, as per the explanation that I have already made, if it is following a center line, if it is following a center line, this center line across the center line, this is the plume, this is the instantaneous plume, this side would be, this is the plume. Okay, if it is the plume, if you can just observe, here so this is what is just to explain you. Say this is around y, this is about y direction, this is about, say this is about x, yeah, this is y. Along y direction it would, as I have already explained, along y it will also have along the center line, this is mu, this is mu, this would be sigma x here, sigma x on both sides, this is plus minus sigma x, as you know. This is where it is, here it is also, you can see the mu here is the at this point a value of mu 1 or mu 2, you can see this mu, this keep at mu 2, this one is mu 1, and this mu 1 you can find out here, this would be having sigma y on both sides, that is what this is, say mu 1. Okay. All I say is there is nothing much to explain other than what I have already said, that in the plume itself, along x y z direction, there will be at different points, the mu would be different at the center line itself. The mu would be mu 1, mu 2, mu 3, mu 4 like this, but mu 1, mu 2, mu 3, whatever the center line values, their dispersion along the value along the x direction, y direction and z direction would be dictated by the dispersion coefficients, that is, we would know of as the mostly the standard deviation that we know of is basically sigma x, sigma y, sigma z along x, y, z directions. Is that clear? So this is what, this is just being pictorially explained. Here you can see this, I think, it does not need an explanation here that, this one is the point here, at this point here is x 0 0 at this point, and this one is, as you can see, this one is x minus y 0. This being the positive direction, this is what is the x y 0, and this one is, as you can further say from this top here, this is, if you can see, the height along this z direction, if it is in the z direction, so you can find is x minus y z. So this is the, so if you are just trying to find out, so this is how this direction would be emphasized. So if you are just trying to observe, say, the concentration at this point x y z direction, then we can see, the ground level concentration, considering z to be 0, considering the ground level concentration, the ground level concentration employing Gaussian Plume equation is for z equal to 0. Remember this, z equal to 0. What I mean to say is, at this, in between, this x and y, here is x1, y1, say this is x1 minus y1 or x2, y2 here, but this is don't have any, or x1, y1 and z0, z equal to 0, x1, x2, y2, z is equal to 0. So concentration at this point, all this ground level concentration, only on the ground level concentration. That is, if you are just putting, if you are just keeping this page showing xy in the plane, this is an xy plane. If it is an xy plane, what we are trying, this is the smokestack. We are only observing the ground level concentration. We are not observing at any point, at any height, x, y, z. We are just interested about the ground level concentration, because what I said is most of the humans and other living beings reside in that particular zone only. So here, as such, as you can see, this the Gaussian Plume distribution can be the concentration at x and y. The concentration at x and y can be written as q divided by pi mu u, the velocity u. Remember, this is u, this is not mu or anything like that, this is u, and sigma y, sigma z. These are the sigma z. This is the typical normal distribution, standard deviation, or we would call them here there's dispersion coefficients, exponential minus h square divided by 2 sigma z square into exponential minus y square 2 sigma y square. Let me repeat it again. This is q, this is the quantity that would be discharged, this is pi is, as you know, 22/7, this is u is the velocity at this ground level, velocity at the average at the stack level, at the stack height level. I'll come back to that. Sigma y and sigma z, this is like this, sigma y and sigma z, then exponential h, this 2 sigma z square, this is y minus y square divided by 2 sigma y square. Okay. Having gone from there, having known this, let me explain these parameters in more detail here. So this one is Cxy. Cxy is equal to the concentration at ground level, at point xy. Remember this, microgram per meter cube. The clue is here. Clue is if the value is given in terms of say tons per day, say ton per day, you have to convert it to microgram per meter cube. Remember this, don't ever confuse this. So mostly the power plant, the discharges would be in terms of tons per day. A power plant, usual power plants essentially emits to the tune of 20 to 50 tons of sulfur dioxide, right? The tons of particulates. So in such cases we have to change it to microgram per meter cube. Remember this, don't ever confuse this. X is equal to the distance directly downwind, this is m. Distance directly downwind, this is y. Downwind along center line, you can write this along center line. This is important. The line of x should be set on the center line itself. Say this is y is the horizontal distance from plume center line. Horizontal, that is from the line of x, the line from x in meter. This is all in meter. Remember this is of great importance. This is a meter. I will tell you why this is of great importance, because most of these sigma x values, sigma z and sigma y values would be given in terms of meters. Q is emission rate. Emission rate of pollutants. Emission rate of pollutants. Here emission rate of pollutants, more than what I said is microgram per second. Say that this is I made a mistake here. Clue is second here. You can see, just make a correction. Tons per day can be only be converted into microgram per second. It cannot be microgram per meter cube. I am sorry. This was emission rate of the pollutants. Essentially, this particular thing would be required here. This would be given in tons per day, and you have to convert it into microgram per second. Just this one is superfluous. This is not much of importance, because this one is important, where this value this value would be essentially be changed by this all these parameters. Okay. So here this is ton per day. If it is given a power plant emitting pollutants at tons per day, it has to be changed into microgram per second. Microgram per second. H, as I have said, H is the effective stack height. Effective stack height, which I have already said as H plus del H. H plus del H. So you have already known. So if it is nothing else is given, you can find it as 1.75 of H. 1.75 of H. This del H becomes almost close to 0.75 H. So H is this, U is average wind speed, at effective height of the stack. This is in meter per second. This is in meter per second. See here, one important thing here is that effective height of the stack. Remember, this is not, this is, see, you will be mostly be given the ground level velocity at the stack. See here, as I have said, if you remember in this, if you just begin here, this one is the ground level value would be given. Say U0 would be given. You have to find out, say that at the center line where it is, say sigma H, say here it is, this is what is H, capital H. You have to find out this value at H, at the point H. Remember this, this would be all given to you in most cases, because this is where you can measure it. We have to estimate that at that stack height UH. So this is UH. UH, you can write it like this, UH, U or UH, U or UH, as you can write this, U or UH, average wind speed at the effective height of the stack in meter per second. This height is, effective stack height is essentially in meters. So in some cases the stack height is given in feet, you have to convert it into meter. You have to convert it into meters for calculation purposes. And sigma y is the horizontal coefficient that is standard deviation, that I have already said, standard deviation along y direction, and sigma z, as you know, this vertical dispersion coefficient, vertical dispersion coefficient, and also the standard deviation along z direction, okay, along z direction. So what we can observe now is along this z direction. Well, there are few important things, as you can see here in this, as we have already considered this expression here. Considering the expression here is this one is given to you, this one is known, this one would be known, this one would be known, these two are relatively unknown, we will find out about them. This is what is question mark here, and this one, as you can see, this one also, h and y will be also be given, h and y would be also be mostly known, right, but we have to find out sigma y and sigma z. How we can find out sigma y and sigma z? There are standard say mostly we use these tables for, but just let me explain this. See, they would be this sigma y and sigma z will depend on atmospheric stability. Atmospheric stability will depend on atmospheric stability, and this would be derived from this atmospheric stability classification. So, we would discuss this, depend on this atmospheric stability classification. You will find most of these textbooks on air pollution, most of the standard textbooks of air pollution, you will find this atmospheric stability classification given, which is, let me tell you about the features of this. Surface wind speed, this is surface wind speed is 10 meter above ground. This is 10 meter above ground. Say this one is, we know as day solar insolation. And this is night cloudiness. This is should be generally strong. This is moderate and slight, and this is cloudy and clear. So, if you just make these distinctions here, see this is less than velocity 2, day solar insolation, say is a solar insolation is, this solar insolation is particularly the strong one. The strong one is, here it says the strong one is like this. Okay, let me explain this day solar insolation, what it says. I'll again come back to this. Let me explain what is day solar insolation. This day solar insolation is, say, particular time of the day when say at a particular point, say where we are measuring this, we are going to measure about the zone where we are going to measure the dispersion. Here, if you see this is where is at this point here, if the sun is 60% above the horizon. So, this is the horizon. If it is 60%, say about this, so here if the sun is between these two zones, say 30, 60, say this 60 degree here, this is when the sun is here. When the sun is here on a clear sky, on a clear summer day, and you are calculating the dispersion at that point of time. So, this one would be known as day solar insolation as to be strong. When this is, when this is between 35 degrees to 60 degrees, say between this position here, when it is clear summer day, on a clear summer day, okay, you have the sun like this, sun is half cast, say the sun is not fully exposed, sun is not fully exposed, say the sun is exposed only this much is dark, say due to cloudiness, this part is dark, few clouds there, and as if the sun is not completely exposed, we would known as this one as moderate. This is a moderate, please some clean, this is strong. This should be summer day, with this one is with this one, the sun at say 35 to 60 degree. This one is known as the broken clouds, this one is known as moderate. And if it is between, say between this, it has to be between 35 and 60 degrees. 60 degrees is the moderate. If it is below than this, if it is below than this, the sun is here, say during the evening time or the early morning time, clear summer day, cloudy, or this is between 15 degrees to 35 degrees and with somewhat cloudy, so this one would be known as slight. Okay, say more or less this is clear, more or less clear or little cloudy sky. This one is known as, this one would be, this is a moderate, strong, moderate, slight, and this is cloudiness, night cloudiness, cloudy and clear. That is cloudy would means that this is between 4 to 8, say of the 8 of the total 8, if 4 out of 8%, that is about cloudy, is this total portion is about more than, if it is more than equal to 50%, we would call them as cloudy. This of the 8 portions of the sky, if 4 portions are covered, say something like this, say if you just try to see the sky like this, and if you observe the clouds are like this, and if these clouds by your own estimation here, if this is covering 4 parts, if these are covering the 4 parts of the 8 parts that you can think of, then this should be known as cloudy. Otherwise, in case of anything less than, if it is generally less than 3/8, it would be known as clear. So 3/8, as you can very well make this calculation to be somewhere about, say, is a 40% or less. Okay. So this is how we are defining. Under such a situation, at a particular wind speed, at these wind speeds that we are talking about, 2 to 3, say 3 to 5, this is in meter per second, remember, 3 to 5, 5 to 6, and say more than 6. If we observe this at a particular, say at a strong day insolation, we find the condition to be A. We find the condition to be A to B. That is what I was talking about, this atmospheric classification, which I said I will bring out later again. So this one is C, this one is C, this is A minus B, A to B, sorry, not A minus B, A to B, B, B to C, this is C to D and D, and this one is B, B, C, C, D, D, then this one is E, F, E, F, D, E, D, 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 D. So, okay. All right. So, you can see this, this is what is, if you remember earlier I said about this the power coefficient, that in the first class itself, when I discussed today in the first class, we said about this power equation, that is about this wind velocity at different heights. That here the P that I used, the P is basically classified in terms of A, B, C, D, and like this, C, D, E, and F. So when we are discussing that P, we have to find out in this manner about this is actually what it means by A, B, C, D, what we would try to explain. So in any case, just for your case or example, so when the wind speed is like 2 to 3 and we have this moderate insolation, solar insolation that I have discussed already, so you will find that the condition prevailing is B. Is it? Okay. So this one A, B, C, D, E, F, that is how we can find out. So in any textbook, say from this, if you are knowing that, if you are knowing from this, just to explain you a little bit on this, here you can see this, you can read this. You can read this, just try to, this would be, you'll find these values very easily any case. If sigma y and sigma z are not given, okay, you can make use of this table. You can make use of this table to find out the value. Suppose you have found out that atmospheric stability class is A, and you are going to measure the distance, say from the stack to a particular position, say at 1 kilometer, the sigma y that you should have is 213. Sigma y that you can see here is 213, isn't it? This is 1 kilometer, 1000 meters from the stack, from the stack, and at a stability class A. The stability class A we have defined clear sky and less than 2 kilometer of velocity of wind. Clear sky, more than the sun at a horizon, sun at 60 degree from the horizon, and so you can find out at that point of time, the stability class as A, and if it is A at 1 kilometer away from the stack, the stability, the sigma y is 213. Similarly, sigma z would be 450. So sigma z would be 450. Here, anything more than this, anything 4, 4, 8, 16, 20, the value of 1953 has to be repeated. So what it basically observes here is, one, it is essentially the Gaussian-Priem distribution restricts itself to explain the situation within, say, 2 kilometers away from the stack. One should not actually try to use Gaussian-Priem distribution, say, more than 2 kilometers from the stack, right, from the position of the stack. So sigma y and sigma z can be found out, and by which you can ultimately estimate the the concentration, the ground level concentration of the pollutant from the emanating from the stack. Okay. Another important thing that is, I would like to explain, tell you here, in many cases where it's so, in many cases we observe that, in many cases we observe that, here we have said Y, but in many cases the ground level concentration, in many cases ground level concentration is implicitly meant to provide the concentration at x 0 0 x 0 0. It is on the center line. It is just on the center line, and it is not y is equal to 0, z is equal to 0. So, the center line concentration, if you are going to find out, you can very well understand that, is in most of this Gaussian plume equation that I have said, the one term reduces because the exponential minus y square divided by 2 sigma y square that is given there. You will observe that y, if y is put as 0, that particular expression reduces to 1. So, we can also find out the value of the ground level concentration like this. There is just a little bit of explanation required about how we find these values. If you just observe now, say this concentration values, ground level concentration values, how these ground level concentration values vary from using Gaussian plume distribution model. This concentration say 1 kilometer, 1 kilometer, 2 kilometer, 3 kilometer like this, distance downwind 4, 5, 6, 7, 8, like this, up to about say 20 kilometers, If you just observe these values, say by using this ground as Gaussian plume distribution model, mostly the plots look like this. What we have found is this is ground level concentration, and we have found out the distance downwind with sigma y and sigma z given. So, sigma y and sigma z, that is atmospheric stability class, is identified, and sigma y and sigma z are given. In such cases, what is the concentration forms like this. So, what is to be explained here is, just to explain here is this, that suppose take this curve, almost these curves are similar looking. What you observe is they are peaking and then finally going down. Okay. So, this is what we observe here, this ground level concentration here is that, as I have said, initially at this, suppose this is where the stack is, suppose for this curve, this is where the stack is. Okay, this is where the stack is. What happens is, initially due to buoyancy, particularly the concentration would be at this point away from, and with the velocity at this point the concentration would be somewhat less, but this concentration certain distance away from the stack would essentially peak. and then it will continuously go down, which is expected, because larger the distance, the concentration would essentially would be reduced. So this is what is just to say, particularly the typical characteristics that we can observe due to using this Gaussian plume distribution model. This model perfectly suits for most of this atmospheric concentration calculation, and which is also another important thing is, say some cases these are all point source, the Gaussian plume distribution is applicable. Remember this, write this, Gaussian plume distribution is specially applicable to point source, as we have said in the case of a stack. This is a point source. It is, say, it is coming out from a point. It is coming out from a point. But this Gaussian plume model also can be used for finding out the line sources. The line sources where it is, this should be, the points are on the line. These are essentially point estimation, but considering that points are in a line, we can find out the concentration in the line sources also. What we do in that case, we just find out the XYZ coordinates we manipulate the XYZ coordinates to identify a particular point, and from different sources the concentration, the likely concentration that would exist there, and the contribution of different sources would be calculated. So here, say if this is the plume model, so here it is, if we are just trying to find out the value here, the concentration value here, say at this point here, so you are only what manipulation you are going to do is, this one is x1, y1, z1 for this curve, this would be x2, z2, y2, z2 for this curve, this point, and this one would be, say, x3, y3, z3. What we essentially do is sigma x1, sigma y1, sigma x, sigma y, sigma z to find out the concentration at this point. So all these concentration values, if all these concentration, cut this, if all these concentration values are C is a summation of C x y z, so where x is equal to 1, y is equal to 1, to z is equal to 1, to x is equal to 3, y is equal to 3, z is equal to 3 can be computed. So we can find out the concentration at this point due to the contribution of the line sources. So point sources can be converted or can be used as line sources. So Gaussian plume distribution is essentially worked out for all these kind of problems, and which is quite applicable and preferably used. Okay, we complete this today's lecture in this. Okay.